4.1, first derivatives and graphs. We are going to save all of our sketching for section 4.4, but you will see me doing some graphing, but none of your problems I expect you to be able to graph until we get to the actual curve sketching part. First derivatives. First off, the first derivative, let me just change to my highlighter here, can tell us the slope of the graph at a particular point. It will give us insight into the shape of our graph. And later in this section, we'll see that it's useful for finding the max and min values of our functions. And it's useful for finding where our functions increase and decrease. So that's where we're going to start. We use sign charts in order to determine the intervals where our function increases and decreases. The first thing that we want to do is find the derivative. So when we find the derivative, and then we set that derivative equal to 0, will tell us where we have that horizontal line. So we set that equal to 0. And when we take the square root, remember we get two values. And that's where we get these numbers, -1 and 1. We create this sign chart. So where it's -1 and 1, our first derivative is 0. Then we test values in each of our intervals in order to find out what sign we have for our slopes. And if we look, our intervals where the graph rises, the first derivative is positive. On an interval where the graph falls, the first derivative is negative. And where it's -1 or 1, this is the first derivative is 0. Okay, so if we look at that, our original function is increasing when our first derivative is greater than 0, and it's decreasing when our first derivative is less than 0. So we can create this nice little table here. So the first derivative is positive. Our original function increases, the graph rises, and it could look like this. It could look like that, or it could be a straight line. When our first derivative is negative, our function decreases, the graph falls. It could look like that. It could look like this, or straight line. So they're just some examples. So let's find the intervals where a function is increasing or decreasing. So first thing we do is find which values of x correspond to our horizontal tangent lines. So we have to do that by finding first derivative, set that, set that equal to 0. So that's the value where our tangent line is horizontal. Then we determine increasing and decreasing. So we do our sign chart. At 4, it's 0. So when it's less than 4, if I substitute back into my derivative, when it's less than 4, we'll test 3. Greater than 4, we'll test 5. When it's 3, we get a positive. When it's 5, we get a negative. So when is it increasing? It's increasing on the interval negative infinity to 4, and it's decreasing from 4 to infinity. So what might this look like? Again, you're not going to be concerned about sketching as of yet, but you can start practicing if you want. So we know one of our values is 4. We need to put that in the original function. So 4 in the original function is 32 minus 16. Okay, so I'm just going to pretend this is 16. And then just test some other values so you get at least some good representation. So if I put a 0 in there in the original function, I get 0. And I know it's symmetrical, so it's going to look like that. And as you can see, increasing, decreasing. Okay, you go ahead and do match problem 1. Again, don't worry about the sketching. Okay, I know my graph is a little rough. So definition of a critical number. So a critical number is that our first derivative is equal to 0 at that value, and or it does not exist, the first derivative value does not exist. They are, but it must be in the domain. So as long as that value is in the domain, it's considered a critical number. We call those values that we were finding before partition numbers. So they're numbers that we just use to see where our values could be changing from positive to negative or negative to positive, etc. A critical number, though, is that partition number that is in the domain. So let's find, so one big thing is not every partition number is a critical number, because if it's not in the domain, then it can't be a critical number. So partition numbers, let's find the partition numbers and critical numbers. So basically, is the partition number a critical number is what we're finding here. So 1 plus the x third, find the critical numbers, the intervals in increasing and decreasing. So we know we have to find the first derivative. set it equal to 0. Is 0 in the domain of the original function? Yes. So it is a critical number. Then what is it doing less than 0? It's positive. What's it doing greater than 0? It's positive. So this is increasing. And since 0 is in the domain, then this is just increasing throughout. So 0 is our critical value, and it's increasing you try match problem number 2. Okay, example 4. Find the critical numbers of f, the intervals on which f is increasing and those which f is decreasing. So we need to take the derivative. Let's first look at the domain. Is there anything, the domain is all real numbers? Because it is a third root, so we can have negatives. So let's find the first derivative. And we have to do the chain rule. When is our derivative? This is now in the denominator. 1 minus x is in our denominator. So when our denominator equals 0, it's undefined. So 1 is our critical value. Let's use CV. Our derivative is not defined there. When it's less than 1, it is negative. Think of putting a negative 1 in here, or even a 0. Okay, and when it's greater than 1, putting a 2 in here, it is still negative. So we are decreasing, but what happens is, if we would graph this, because our 1 is not not defined as the first derivative, this would then become a vertical tangent. Okay, so go ahead and you try, this should say match problem number 4, sorry. You go ahead.